Welcome to Math 201. This is our first of two lessons on section 4.3, optimization and modeling. Let's say a farmer has 400 feet of fencing to enclose a rectangular corral. To save money and fencing, he intends to use the bank of a river as one boundary of the corral. Find the dimensions that would enclose the largest area. So we have a few possibilities. I'm just going to draw like a few of them and calculate the areas. So we've got a river, right? That's going to be one side of our corral. And we have 400 feet of fencing. So we could make a long, skinny corral. Like we could come out, say, 10 feet. So we've used 20 feet of fencing, right? We've come out 10 feet. And so we used 10 feet here and 10 feet here, which means we have 380 feet to connect. And the area of this corral would be 3,800 square feet. So we could do long and skinny. Let's make it a little fatter, right? So I'm going to have my river. And instead of coming out 10 feet, like maybe I come out 25 feet. Okay. And that means I've used 50 feet of fencing, which means I have 350 feet left to make the third side. Okay. So the area of this corral would be 350 times 25, which is 8,750 square feet. So if you were just choosing between this option and this option, we would choose this option. It's got a bigger area. But there are so many options to choose from. Like, what if I come out 50 feet? So I'm going to go 50 feet, 50 feet. So I've now used 100 feet of fencing, which means I have 300 feet of fencing remaining. And the area of this corral would be 50 times 300, which is 15,000 square feet. That's way better than this one. But at some point, I'm going to start getting long and skinny. Let's say I make my sides that come out away from the river 180 feet. That means that the third side, 180 and 180 is 360. So I have 40 feet left to make the third side. And the area of this corral is 7,200 square feet. Okay, so I have infinitely many options to, for instance, who's to say that 30 feet isn't better than 50 feet or 60 feet isn't better than 50 feet? I can't check every possible option. Um, I mean, I guess I could check every possible integer option, but then there's like, what if the answer is the maximum area happens at 52 and a half feet or 52 and a third feet? Um, I can't check every single possible option. This is where calculus helps us answer. So let's draw a picture. So we've got the river, and I don't know how far out I need to come. We'll call it X. Okay, and then we have this third dimension, Y. Okay, so I want to maximize the area of the corral, which is X times Y. Okay. But I have too many variables, right? X times Y, that's too many variables. This is called single variable calculus. I should only have one variable that A depends on. So I need to write down over here, I have what's called a constraint. And that's that I have 400 feet of fencing, right? So I know that 2x plus y is supposed to be 400. And let's solve this thing for y, 400 minus 2x. So then I can go into my equation that I want to maximize, and I'm going to replace the y with a 400 minus 2x because those things are equal. So area is x times 400 minus 2x. And this is what I want to maximize. Let's distribute the x. So I have negative 2x squared plus 400x. So to maximize, I want to find the maximum value on that graph, but I need to consider the domain. The domain of A of X, okay? So domain means smallest possible X to largest possible X. Okay, so looking at my picture, what is the smallest X value? Like the smallest we could come out from the river. We did, in the previous slide, we came out 10 feet, but we could have come out 5 feet or 2 feet or 1 foot or half a foot. So the smallest possible X would be 0, right? So it doesn't make sense, like you couldn't actually do that, but we're gonna say 0. In the case that X is 0, we are not coming out from the river at all. You're going to use all 400 feet of fencing right along the river. It's just going to be a straight line with no depth to the corral, no width to the corral. So it would have 0, an area of 0. I mean, it would be a stupid way to use your 400 feet of fencing to just have a straight line along the river, but I suppose you could do it, right? And then the largest value you can make X is if you use all of your fencing to come out and have no width along Y. So all your fencing is used in this vertical. You would do 200 and 200 with no space in between. So the largest X would be 200. Okay, since the domain is closed, to maximize, we just plug the endpoints and the critical points into A to find the largest area. So let's find critical points. Remember my area function was negative 2x squared plus 400x. So A prime would be negative 4x plus 400, and we want to know when that equals 0. So that happens when x is 100. So there's our only critical point. So then I'm going to make an XY chart and have x and then area. And I'm going to plug in my endpoints, 0 and 200, the endpoints of the domain, and the critical point 100, and calculate the area for each of those. So if I put in a 0 for x, my area is 0. And if I put in a 200 for x, my area again is 0. And if I put in a 100, I get 20,000 square feet. So that means this is my max. So the maximum possible area is 20,000 square feet. And it happens when the dimensions are 100, x is 100, and y is 200. So key ideas and steps for these kinds of problems are draw a picture, find two equations, one that you're going to maximize or minimize and one that's a constraint. Write the equation to optimize in terms of one variable only and find its domain. Then you optimize. If it's a closed domain, find critical points and compare the function values at the critical points and the endpoints of the domain. If it's an open domain, find and classify your critical points, find the behavior at the endpoints, compare values to find the max and or the min. Okay, we've come to our first activity. Pause the video, try these problems. When you're ready, press play and we'll go over them. Park planner Don is building a fenced-in dog park for the neighborhood. He wants there to be two separated areas that share a side. one for the larger dogs and one for the smaller dogs. He has 200 feet of fencing available. A rough picture of the two areas is provided below. Note that L corresponds to the entire length of the side, not just half. So I'm just going to make that clear by drawing a line that shows that whole side is called L. Write the area in terms of both variables L and H. So the entire area enclosed here is just H times L. So area equals L times H. Identify a constraint equation and use it to rewrite the area in terms of one variable alone. So my constraint is the amount of fencing I have. I have 200 feet of fencing, and that has to cover 3 lengths that are H and 2 lengths that are L. So 2 L's and 3 H's have to add up to 200. That's all the fencing I have. Um, and I could solve for one of these variables, say H. H is going to be 200 minus 2L over 3. And then I'm going to use that in my A equals L times H equation. I'm going to replace my H with this expression. So this is L times 200 minus 2L over 3. Okay, just to make this easier to take a derivative of, which I'm going to have to do in my next step, I'm going to break this one big fraction into the sum of two fractions. I'm going to divide this 3 into each term of the numerator. So this is going to become area equals L times 200 thirds minus 2 thirds L. And then I'm going to distribute the L. I'm going to distribute this L into the parentheses. So area is going to be 200 thirds L minus 2 thirds L squared. Okay, in the next step, I want to specify the domain of the area function. Based on the constraint equation, there are definite upper and lower bounds. All right, so I have redrawn the picture of our dog park, and my domain is the set of all input values for the original function. So the function that I'm looking at is A equals 200 thirds L minus 2 thirds L squared. I want constraints on L, like what is the smallest L and the biggest L? Okay, so I'm going to do smallest L to the biggest possible L. Okay, so if H was 0, right, if we didn't come out at all, then I would have 200 feet of fencing with which to build 2 L's right on top of each other with no space between them. So 100 is the longest that L can be. That happens when H is 0. Okay, and then the smallest L can be would be 0. And I would use all of my fencing on 3 H's that are right on top of each other with no space between them. So it would have to be 0 to 100, smallest L to the biggest L. Okay, now I want to find the dimensions L and H, which provide maximum area. So largest area will occur at an endpoint or a critical point. So let's start with critical points. We'll find those. So we're going to take A prime, which is 200 thirds minus 4 thirds L, set it equal to 0. And we get 200 minus 4L equals 0. Just multiply both sides by 3. And then we get 200 equals 4L, so L is 50. All right, so to determine if that is if that will give me maximum area, I'm just going to set up a little XY chart, X and area of X. I'm going to put in the endpoints of my domain, which are 0 and 100, and my critical point of 50. So I'm plugging these X values into the area function. I want to know what the area is at each of these because I want maximum area. So I'm pick the biggest one. So if we put in a 0 here for L, I get area is 0. And if I put in a 100, we also get 0. And if you put in 50 for L, you might need a calculator or write that out, but we get 5,000 thirds. So this is my maximum area. Okay, so we can write a sentence. The max area is 5,000 thirds square feet, and it occurs when L is 50 feet, and then H would have to be, if L is 50, then we've used 50 and 50 is 100. So I have 100 feet left to put into 3 equal pieces, so 100 thirds feet. Okay, next example. Find the area of the largest rectangle that can be inscribed below the curve y equals e to the negative 2x squared, but above the x-axis. So note an inscribed rectangle means it has 2 corners on the curve and 2 corners on the x-axis. So I'm just going to draw a random rectangle. Maybe I'll go here and here as my 2 x values on the x-axis, the 2 corners on the x-axis. We're going to go up to the curve and inscribe a rectangle. So this rectangle is inscribed by the x-axis and the curve. And I want to know, where should I put these x values? What x value will make this have the largest possible area? So if I want to calculate the area of this green rectangle would be base times height. Okay. And the base is 2x because it's x to the right of the x-axis, of the y-axis, x to the left of the y-axis. So this whole distance is x plus x, 2x. Okay, so the area of my rectangle is base times height. And that would be the base is 2x. And the height of this rectangle is the height of the function. Okay, so if x is my input value, the y value right here I could get by plugging into the curve because this point is on the curve. This is the point x comma e to the negative 2x squared. So my y value is e to the negative 2x squared. That's the height of the rectangle. All right, so that's my area. Its domain, smallest x to biggest x, right? So the smallest x would be 0, right? So if I just put x here, I would have a vertical line going up to the curve and it would have an area of 0. Okay, and the largest x would be, there sort of is no largest, right? I could keep moving this to the right forever. This asymptotically approaches the x-axis, so technically I can keep going forever. So I'm going to put infinity here and change that to a round bracket. So I know that the max area will occur at a critical point or an endpoint of the domain. So my function that I'm trying to maximize is a of x equals 2x e to the negative 2x squared on the domain 0 to infinity. Okay, so it's going to happen, the maximum will happen at a critical point or an endpoint. So the critical points, those happen when the derivative is 0. So I'm going to take a prime, which I'm going to have to use the product rule for. This is f and this is g. So we're going to have f prime g, so 2 times e to the negative 2x squared plus f 2x times g prime. And the derivative of e to the negative 2x squared would be e to the negative 2x squared times the derivative of negative 2x squared, which is negative 4x. And I want to set that equal to 0, and solve it. So what I notice is that this term and this term both have an e to the negative 2x squared. In fact, they have a 2e to the negative 2x squared. So let's factor that out. And I'm left with 1 minus 4x squared. Okay, so either 2e to the negative 2x squared equals 0, or 1 minus 4x squared equals 0. This is never, and this is x squared equals 1/4, so x is plus or minus a half. So there are my critical points. So to summarize, we're trying to maximize a of x, the area of a rectangle, given by 2x e to the negative 2x squared, on the interval from 0 to infinity, and I have critical points at plus or minus a half. Okay, so I'm going to look at a XY chart. I can put in 0, the first endpoint of the domain. I can put in 1/2. I don't need to think about the negative 1/2 because in the picture that I drew, x represented a length, a distance. So I don't need the negative 1/2. So I'm just going to put in 1/2. And then the other endpoint of my domain is infinity. Okay, I can't plug infinity in, but I could take a limit as x goes to infinity. But let's see, if I put 0 in here, I get 0. And if I put a half in here, I get 2 times a half is 1. A half squared is a fourth times negative 2 is negative a half. So I get e to the negative 1/2. And if I put in infinity, which I can't really put infinity in, but I could take a limit, right? I could look at the limit as x approaches infinity of 2x e to the negative 2x squared. And 2x goes to infinity, but e to the negative 2x squared goes to 0 very fast. Okay, and then that ends up going to 0 overall. So my maximum area is e to the negative 1/2, and it occurs when x equals a half. Okay, we have reached our second activity for the lesson. Pause the video, try these problems, press play when you're ready to go over it. Okay, for number 1, we want to find the area of the largest rectangle, which can be inscribed inside a region R, where R is defined as being enclosed by the lines x equals 0, which is the y-axis, y equals 0, the x-axis, and the curve y equals 1/9 x squared minus 2x plus 9. So that's this curve right here, this quadratic. So below is a diagram for the region R. This whole region is R, and I'm inscribing a rectangle R inside of it. So I'm going to have one corner at the origin, and then one corner on the x-axis, one corner on the y-axis, one corner on the curve. So you can assume that the rectangle will have sides parallel to the axes. So write the area in terms of the variables x and y. So this point on the curve we're calling x comma y, which means you go over x, up y to get to that point. So my area is x times y, base times height for the rectangle. And then I want to rewrite that area in terms of only x. So remember that y is this formula. Okay, y is 1/9 x squared minus 2x plus 9. So I'm just going to have area is x, and instead of y, I have 1/9 x squared minus 2x plus 9. Okay, first question on the next slide is what's the domain of a of x? So remember, domain is the set of all input variables. So what values of x make sense to plug into this formula? So the smallest x value to the biggest x value. Smallest x value would be 0, where you'd have a tall, skinny rectangle with no width whatsoever. And the largest x value would be 9 because you hit the end of the region R. Okay, so 0 to 9 is the domain. Okay, and then we want to find the dimensions of the rectangle with maximum area. So in order to do that, we start by finding critical points, right? Maximum, the global maximum will occur at either a critical point or an endpoint of the domain. So I need to know the critical points. So remember my formula was a of x equals x times 1/9 x squared minus 2x plus 9. And then I'm just going to distribute that x. So a of x is going to be 1/9 x cubed minus 2x squared plus 9x. So critical points happen when the derivative is either undefined or a 0. So when I take the derivative of this, I get 3/9 x squared, that's 1/3 x squared, minus 4x plus 9. And I want to know when that equals 0. So to solve this, I could use the quadratic formula, but I think what I'm going to do is multiply both sides by 3, just to make the coefficient on the x squared a 1. So I have x squared minus 12x plus 27 equals 0. And then that factors pretty easily. We have x minus 3 times x minus 9. And we get x equals 3 or 9. Both of which are in the domain 0 to 9. So I need to check out both of them. So I'm going to make an XY chart, x, area of x. I'm going to put in the endpoints of the domain and my critical point. Okay, I'm only putting in the 9 once. It's a critical point and it's an endpoint of the domain. We only need to know the y value one time. Okay, if I put 0 into a of x, this is my a of x function. If I put a 0 in here, I get 0. If I put a 9 in there, I get 0. But if I put a 3 in, it turns out I get 12. Okay, so just use a calculator. You can just use a calculator to get these a of x values. I'm just plugging x's into the formula a of x. So 3 comma 12, that's going to be my global maximum. To summarize, we say that the max area is 12 and occurs when x equals 3 and y equals 1/9 times 3 squared minus 2 times 3 plus 9, which is 4. Number 2, there is a study lounge in your house with strange dimensions. The room is enclosed by the curves y equals 0, which is the x-axis, and y equals 9 minus x squared over 4, which is this parabolic curve. The large windows on the rounded wall of the lounge give a great view of the quad, but the wood floors in this room are particularly cold in the Massachusetts winter. Your house council has decided to buy the largest rectangular area rug they can to make the lounge more welcoming in winter months. So this shaded region is the area rug. They're trying to buy a rectangular area rug. It's got to be a rectangle, and they want it to cover as much of the floor as they can. Maximize the area. So they want to know what XY would give maximum area. So the area of this rug in terms of both X and Y, why is it not just XY? So if this point is X comma Y, this point is negative X comma Y, right? Which means this distance is X and this distance is also X. So that whole distance is 2X. So area is actually 2X times y, or just 2xy. Okay, rewrite the area in terms of only one variable. So I already have it written as 2xy. And then I can rewrite it in terms of one variable because I have a formula for y. It was given in the problem. It was 9 minus x squared over 4. So this is going to be 2x times 9 minus x squared over 4. And I'm going to multiply that out because my next step is going to be, well, 2 steps from now is going to be to take the derivative. So I'm going to distribute that 2x and I get 18x minus 1 half x cubed. Okay, to find the domain of the area function, that is what values of x can I plug into this function that makes sense? Okay, so the smallest x I can plug in and the biggest x I can plug in. Okay, I just grabbed a picture of our room and rug again. And the smallest x can be, like, so x is how far you go over from the origin to get a point on this curve. So the smallest it could be would be 0. So you don't move at all from x equals 0. You just go up to the curve here. You're going to have an area that has 0 because you have no width, but technically the smallest x can be a 0. Okay. And then the largest x could be would be 6. That's as far over as you can go. So if you have an x value of 6, you can go 6 and 6. Again, your area is going to be 0 because you can't come out from the wall at all if you go all the way to 6. But technically 6 is the largest the x value can be for this rug. Okay, next I want to find the dimensions of the rectangular rug, which would cover the greatest area. So the maximum area is going to happen at a critical point or an endpoint of the domain. I've already got the domain endpoints here. I got to find critical points by taking the derivative and set it equal to 0. So a prime of x is going to be 18 minus 3 halves x squared. We set that equal to 0. And we get 3 halves x squared equals 18. So x squared equals 12, and x equals plus or minus root 12. Okay, I'm going to ignore the negative because it's not in the domain. Okay, so ignore negative root 12, it's not in the domain. I am just going to make an XY chart for x and area of x. So for each x value, I'm going to calculate the area of the rug, and the x values are going to be my endpoints of my domain and my critical point that is in that domain. So I'm going to have 0, root 12, and 6. And when I plug these values into the area function, the endpoints give me 0. Okay, we already talked about that when we were figuring out the domain. We were like, well, technically x could be 0, but you'd have no area. Technically x could be 6, but you'd have no width to the rug, so the area would be 0. Okay. If I put in a root 12 here, I get 18 root 12 minus 1 half times 12 root 12, which would be 12 root 12. And this is going to be my max. Okay, so my max area is 12 root 12, and it occurs when x is root 12 and y is, I can calculate this by plugging root 12 into the formula for y, which was given in the original problem. I get 9 minus root 12 squared over 4, which is 6.